Hello, thank you for joining us today to hear about JJC Enterprises Horus One Martian Transfer Vehicle. This will be presented by Chloe Cochran, Jesus Garcia, and me, Julia Metz. So, our agenda for today, we are going to start with the history of JJC Enterprise, then we will move into the mission overview. Chloe will cover orbital maneuvers. I will then explain the propulsion system used on this transfer vehicle. Then Jesus will talk about the vehicle structure. We'll move on to aerodynamics and smaller onboard systems before doing a final overview. So, Chloe.
Hi, I'm Chloe Cochran, and this is a history of JJC Enterprise. JJC Enterprise was founded in August 2020. Our chief engineers are myself, Chloe Cochran, Jesus Garcia, and Julia Menzel. This program is named after Horus, the ancient Egyptian god. He's the ancient god in the form of the falcon with a sun as its right eye, which represents power and quintessence. He's a god of healing, protection, the sun, and the sky. And for these reasons, we believe that these attributes align perfectly with the Horus One mission itself. On the bottom part of our program's logo, you can see the words Bellum, Xylem, and Praesidium. These words mean war, sky, and protection. In this section, I'll be going over the mission overview with you. So with this program, like I mentioned, our initial goals are to design a mission to Mars, an entirely new reusable transfer vehicle. Once we get to the Martian surface, we're going to travel to and from that surface and to and from shuttling from an orbital space station, which will carry supplies and eventually humans. Our final goal for our program was for human settlement on the Martian surface. With a program this size, there's obviously many future impacts, but I think the top two of importance are future human settlement on Mars and sustainability in space missions, as this is a focus on reusability. So with this program, we had four major factors to go within our design approach, which includes safety, cost efficiency, weight, and reusability. So with all these different factors, I think the main focus of our program was just optimization as a whole. So with safety, obviously the journey to Mars presents numerous hazards and challenges, including intense temperatures, radiation, and potential for equipment failure. Therefore, we're going to go through rigorous testing and quality assurance to minimize this risk of accidents or malfunctions. Additionally, maintaining high safety represents initial confidence in public and stakeholders, fostering continued support for our Mars exploration initiatives. We clearly want the people to be behind what we're working on, and that goes for hopefully increasing our budget in the future if need be, or just public trust. Another main factor of our design approach is reusability. So a reusable launch vehicle offers numerous advantages that are important for the success and sustainability of our endeavors. Reusability drastically decreases the overall cost of transportation by allowing the same vehicle to be used for multiple times. This cost efficiency aspect of reusability is highly significant in the context of the Horus One program, where every extra kilogram of payload creates an additional expenses due to intense distance of this journey. Another focus we had within our design approach is cost efficiency, which kind of goes hand in hand with reusability. Cost efficiency is crucial for this program. Financial resources required by Horus One are significant, therefore maintaining a balance between performance and cost is imperative. Every aspect of this mission, from spacecraft design to testing, must be optimized to ensure that all objectives are achieved within our current budget. By prioritizing cost efficiency, Horus 1 will make Mars exploration more sustainable and accessible for future human settlement. The final part of our design approach is our focus on weight. So, weight efficiency of launch vehicles is extremely significant. Every extra pound obviously will add to that cost of our payload in terms of fuel, in terms of safety. Um, Therefore, prioritizing weight, efficiency, and launch vehicle design is crucial for the success and affordability of Mars. So this right here is Eric Volnop's concept of operations. I'll move myself over. So our program can kind of be divided up into three different phases. The first one is the launch from Earth. This will be an initial launch from the Kennedy Space Station. This location is a very desirable spot to launch from because it allows for eastward trajectory, ensuring that the vehicle will take advantage of Earth's natural rotation. By taking advantage of the Earth's rotation, the vehicle experience an increase in velocity, which helps with the optimization of fuel. This also is a great location because it minimizes the risk of heavily populated areas in case something poor happens. The ball of our vehicle won't crash or land onto where many people are located. The next phase is our journey to Mars. So I will talk about it a little bit more in a second, but we're going to be using the method of patch conics. And that's going to focus on optimization as well, because that's going to go from using the spheres of influence of the Earth and the Martian surface to our advantage. We're also going to focus on our refueling station at Lagrange Point 2, which I'll talk about a little bit more. And then finally, the third phase is going to be that shuttle between the Martian surface and orbital space station. We're going to have a circular orbit around the Martian equator. Most of NASA's research and landings have actually already occurred on the Martian equator. So that allows for all of the prior research we've done on the Martian surface to be used to our advantage, which also will reduce costs in the end. Additionally, Mars spins faster at its equator, which will give a rocket traveling the same direction another boost in velocity, which once again will help with our cost optimization.
So, moving on from ConOps, we will talk about the human rating requirements. So, these 6 requirements include failure tolerance. So, no 2 failures may result in crew fatality or permanent disability. There's also software failure requirements saying that there will be insurance that systems will be designed with capabilities to prevent dangerous behavior of critical software in which a catastrophic event results. Then the third requirement is in regards to human error. So no single human error during operation will result in a catastrophic event. While the manual control human rating requirement says that crew will have the ability to manually control the flight path and attitude of the vehicle. As for emergency systems, they're not to be considered to satisfy failure tolerance requirements. However, they do include fire suppression, crew escape, and other systems that may be utilized to mitigate failure. Then we have crew escape and abort systems. So the vehicle will be able to provide abort capability from the launch pad until Earth orbit insertion. As far as the budget, this mission will be 20% of NASA's 2024 fiscal year budget, so around 1.58 billion, which might be shocking to some, but in reality, that's what we have to consider for this mission of this scale and to prepare for human settlement on Mars. So there are going to be some recurring costs, and that's going to be the mission operations, research and development, also employee salaries, and as well as testing of the vehicle. Now, for the non-recurring costs, that's going to be the initial spacecraft development, launch site preparation, mission design and planning, and all the ground support equipment. So this graph that you can see on the right-hand side of the screen, that is the budget of NASA's fiscal years over the past, looks like 11 years. So now we have our timeline, and this outlines that we are currently in the beginning design phases. In the next few years, we'll be moving to aerodynamics and electronics design more so. And then starting in 2026, we will begin testing, structural testing, aerodynamic testing, then moving forward to electronics testing, subsystem testing. And by 2035, all of our flight tests will be completed.
I'm now going to go into a little bit more detail about the orbital maneuvers of the Horus 1 program. So like I previously mentioned in the ConOps slide, we're going to be breaking down this mission into 6 different sections, which are on the left-hand side of the screen. In order to focus as an optimization problem of the program itself, we'll be using the Earth and the Martian spheres of influence to help optimize fuel efficiency and calculation efficiency as well. The method of batch conics will be used in order to simplify this problem into basically a two-body problem. So for the first phase of our orbital mechanics calculations, we're going to go from launch from the Kennedy Space Station into a low Earth orbit. We're going to be focusing on taking advantage of the Earth's natural rotation, which, like I previously mentioned before, that's to help with an increase of velocity. It's also going to provide a safe path for vehicle stages to fall toward the Earth if anything happens. I did make a couple assumptions while focusing on these orbital mechanics calculations, based on prior research with NASA's current system. I said the drag loss type is going to be assumed to be 0.5 kilometers per second. Gravity will be assumed to be 1.5 kilometers per second. Thrust loss type is going to be 0.25 kilometers per second, and the total loss will be 2.25 kilometers per second. With each phase of my orbital calculations, I focus on finding that delta V value, which is that formula will be seen in the paper provided files. The next part of our orbital mechanical calculations is going to be the low Earth orbit to hyperbolic orbit calculations. Due to the Earth's sphere of influence, the launch vehicle would need to go from a low Earth orbit into a hyperbolic orbit. And then with this calculation, we're also going to be finding a change of V to transfer to the next phase of the calculations. So once we go from a hyperbolic orbit, we're going to go into a Hohmann transfer. And that's basically that slingshot method that I feel like Hollywood cinemas often talk about. But in order to escape this Earth sphere of influence, the launch vehicle will have to have an exact and exert more thrust in order to transfer from the hyperbolic orbit and around the Earth spheres of influence into a Hohmann transfer. Hohmann transfers are often used just because they are most energy and fuel efficient. So due to the astronomical distance to Mars, this transfer will be using Hohmann transfers in order to efficiently continue our journey to Mars. After that hyperbolic orbit to a Hohmann transfer, we're then going to be focusing on Hohmann transfer back to hyperbolic orbit, similar to what we saw when we were leaving the Earth's sphere of influence. Before beginning that circular orbit around the equator, the launch vehicle will have to transfer its trajectory from this Hohmann transfer into that hyperbolic orbit. From there, we're going to go from a hyperbolic orbit to an equatorial circular orbit. Since the journey is so long, it's going to be 219.69 million miles to Mars. It's going to focus on in-source utilization. This concept of in-resource utilization definitely focuses on optimization of cost and efficiency. So we'll be focusing on Lagrange point 2. Lagrange point 2 is highly advantageous because it is as opposed to other Lagrange points for many reasons. It has an uninterrupted line of sight to Earth and the Sun, making it a preferred place for communication with Earth, which is incredibly important when you're having a launch vehicle journey this long of a distance. Additionally, the station's proximity to Earth results in minimal signal travel time and enhances the launch vehicle's communication capabilities with mission control on Earth, which we'll talk about in a little bit. And then from that equatorial circular orbit, we're going to be shuttling to and from that surface back to that station, like we mentioned before. In the bottom right-hand corner of the slide, you can kind of see all the different locations NASA's focused its research on. And that's genuinely why we are focusing on equatorial circular orbit, just because that's where all the money has been invested so far. So we thought it would make the most sense to continue focusing on that equator. For our entry, descent, and landing methods, it was vital to talk about this just because the Martian atmospheric pressure ranges from 6 to 7 millibars, which is less than 1% of the Earth's atmospheric pressure. Due to this extremely thin Martian atmosphere, re-entry methods for transfer vehicles need to be considered for this program. For example, if Mars had a thicker atmosphere like Earth, landing the vehicle will be straightforward by making use of aerobraking and parachutes. However, the thin Martian surface is thick enough to require the managing of heat of re-entry, and rockets are needed to land large aircrafts. A heat shield will also be used to slow the vehicle down in order to safely land the vehicle on Mars. However, due to the extremely small density of the Martian surface as opposed to the Earth surface, a wider heat shield will be used. We also focus this in our thermal protection system, so we'll be using phenolic impregnated carbon ablator pica heat shield.
Summarized concept of our mission is being shown in this fly sheet, especially covering the mission capabilities, launch details, and vehicle specifications. In terms of mission capabilities, the initial mission of this is a transport to the Martian surface through the Starship Super Heavy. And once that is completed, and if successful, then our next mission will be to transfer cargo and humans between the Martian surface and orbiting space station. In terms of the launch details, we are set to launch in the fourth quarter in 2035, and the launch site will be the Kennedy Space Center, located in Florida. In terms of the vehicle specifications, we have a 14-meter tall structure that is composed for a single stage. This structure is powered by 2 SpaceX Raptor engines, which by themselves are also powered by fuel of liquid oxygen and methane. Combined, they provide 460 tons of thrust, and overall, the whole structure has a mass of 200,000 kilograms.
Okay, now we're going to move on to the propulsion system of this transfer vehicle. Ultimately, the decision was made to use the SpaceX Raptor 2 engines. So, a trade study was performed to determine which engine would be best qualified. And so, it was between the SpaceX Raptor 2, the SpaceX Merlin 1D, the BE-4, RD-180, and RS-25 engines. These engines were compared against their thrust-specific impulses, engine sizes, and their cost. And ultimately, like I said, that the SpaceX Raptor 2 is going to be the best engine for this mission. As you can see here, these are some of the characteristics of this SpaceX Raptor 2 engine that will be used in the calculations for the remainder of this project. Now, going into a little bit more detail about the SpaceX Raptor engine. It's a full flow staged combustion engine with 2 separate turbines for fuel and oxidizer, allowing for separate and partial burning to generate a high pressure and high temperature gas mixture. This mixture is then fed into the main combustion chamber where it is fully burned and produces high pressure exhaust gases. Exiting through the nozzle, the exhaust gases generate thrust. So as you can see in this image, that depicts the explanation I just gave. Now for fuel generation. On Mars, we are going to generate our own fuel so we don't have to continually spend money and send up fuel for all of our missions. So the main propulsion system, the SpaceX Raptor engines, will use liquid oxygen and liquid methane. It would not be feasible to continually transfer these propellants for future transfer missions, so both the oxidizer and the fuel will be produced on the Martian surface. Now, to generate oxygen for this mission, a device developed by NASA will be used. So this device is often referred to as MOXIE, which stands for the Mars Oxygen In Situ Resource Utilization Experiment. The system is necessary for humans to survive and leave on Mars. So, MOXIE works by extracting the carbon dioxide from the Martian atmosphere. Then, after it pressurizes the air is then heated to 800 degrees Celsius, which allows for an electrochemical process to take place where one oxygen atom will separate from each molecule of carbon dioxide at this point. Now, this instrument has been proven to be the most reliable option as it has been used during all seasons on the Martian surface. It's already been tested. The atmospheric conditions on Mars are more variable than Earth, where the density of air can be greater by a factor of 2 during the year, while the temperature can vary by 100 degrees Celsius. With all of that being said, the maximum efficiency of MOXIE provides 12 grams of oxygen an hour with at least 98% purity. So there are plans to enhance this MOXIE device by providing a liquefying method and storage for the oxygen on the Martian surface. The system has already been used on the International Space Station to provide breathable oxygen from water, and by using electricity from solar panels to produce carbon dioxide, hydrogen and oxygen are generated. These elements will react with the carbon dioxide and produce methane and water. And to run more efficiently, zinc will be used as a catalyst for this process. This process is also, it's very important to note that this process skips the water to hydrogen step and converts carbon dioxide to methane directly. So ultimately, to achieve full reusability of our SpaceX Raptor engines, they need to run clean and require low maintenance with a simple turbo pump seals and low pre-burner temperatures. Luckily, the Raptor engines use methane, like I said, which burns clean and cool. This allows for increased reusability and it helps to expand the life cycle of that engine. Now, these specific engines ignite by the use of dual redundant spark plug lit torch igniters, while coaxial injectors and propellants or send propellants into the combustion chamber. So again, this is just a fully reusable engine because of that methane that burns cool and clean. So for the secondary and auxiliary propulsion, we're going to be using a cold gas reaction control system. So the combustion chamber consists of the nozzle where the thrust vector control and gimbling take place. So the thrust vector control maintains the attitude of the vehicle by redirecting the exhaust gas, which flows from and generates a vehicle's torque. So the system will account for the vehicle's center of mass shifting with propellant burn, and the SpaceX Raptor engines are capable of gimbling at 15 degrees on the X and Y axes, which is much more than engines of similar size and power. Now, okay, so a cold gas reaction control system will be used for the liquid main engine control. This will be used to control a vehicle's attitude, so roll, pitch, and yaw. There was a design decision made to couple the RCS thrusters together, enabling the spinning of the aircraft without adding any lateral velocity. Additionally, we will use reaction wheels to allow the vehicle to make slow and steady turns. And by changing the speed of these four wheels, the vehicle will be able to turn in different directions. So the combination of the RCS thrusters and the reaction wheels allows for the opposition of forces, which positions the vehicle in our intended orientation. So the liquid main engine control includes a system of valves, pumps, and regulators, while the propellant feed system controls the fuel and oxidizer tanks. And the combustion chamber controls the igniter and fuel injector, as I previously had said. The nozzle is also going to work to direct the flow of these exhaust gases, and by regulating the flow of propellant into the combustion chamber, we can control thrust. So now we're going to move on to the propellant tank pressurization. This is essential to mission success. Pressure regulation process ensures that propellant can be fed to the engines. For our Martian transfer vehicle, a helium tank pressurization process has been selected. So you can kind of see this process in the diagram on the right-hand side of the screen. Now, helium is an inert, non-flammable gas and is lightweight, which allows for increased safety and the potential for more cargo mass. And Jesus will present on vehicle structure.
So for our vehicle structure, we started originally with a materials trade study. And this is an in-depth analysis to kind of best decide what materials should our vehicle structure be mostly made out of. Um, we initially compared an aluminum alloy, a titanium alloy, stainless steel, titanium, and fiberglass composite. We performed an entire trade study, and we focused on six primary weighting factors, including the safety risk, the weight of the material, corrosion, total lasting time in use, cost, and maximum temperature the materials can withstand. So after performing this analysis, we saw that titanium alloy structure was just overall the best fit for our structure. For many aspects, primarily, titanium alloy structures typically have low material weight. These alloys have an extremely high strength to weight ratio, which allows this material to provide strength comparable to steel, but at a much lower weight. And like I mentioned, weight efficiency is crucial within this program. Another primary reason why the titanium alloy was selected was because of its safety aspect, which is another factor for our design approach. Titanium alloys have high fatigue and resistance, as well as resistance to corrosion, which makes them an extremely safe choice, which obviously is safety is a top priority within our program. Additionally, the cost efficiency of this alloy has always been proven to be beneficial. Titanium alloys can be more expensive than other materials, but their high strength and durability will lead to cost saving over time. Since this program is going to be lasting around 11 years, and then hopefully continuing research in the future, cost efficiency, while in the beginning it is a little bit more expensive than other materials, the durability and other advantages of this material will lead to cost savings over time, which that does matter within long-term programs like Horse One. And finally, titanium alloy structures have high temperature resistance. Um, this high temperature strength and resistance to thermal expansion will make them suitable for withstanding extreme heat, which is going to be generated during launch and re-entry into the Martian atmosphere.
The structure that will be attached to the SpaceX Starship originally was going to be 20 meters tall and have a maximum width of 8 meters. Later in the mission, the payload size was decreased to 14 meters since that is the capability of the Starship. The vehicle was designed with the main purpose of being capable of landing on the Martian surface and being able to take off from it to return to orbit. Though it is in its first stages, the vehicle will use two liquid rocket engines due to the water obtained from Mars that will allow the mission to produce its fuel. Said engines will fit in a 4-meter tall and 8 meters wide cylinder chamber, but this is customizable to fit the engines. It will also have a capsule that will transport the crew and the most valuable tools and resources. And this cabin will have the dimensions of 6 meters in height and 6 meters in diameter. Finally, the third section of the vehicle will be attaching the rocket engine to the capsule. This structure will not only hold the weight of the capsule, but it will also withstand the thrust of the propulsion and, in addition, will store the avionics and electronics of the Horus 1 vehicle, not to mention the liquid oxygen tank and the 4 methane tanks. Circling back to the capsule design, the capsule will be a 6-meter tall and 6-meter wide structure that will keep the crew and its additional content safe. It will have a thickness of no less than 5 millimeters, which will be a combination of various layers, each with a purpose, but the majority of that thickness will be the fuselage made out of titanium alloy, with added Kevlar in certain regions for added protection, as well as several spotted additions of carbon composite reinforcements. These materials were selected after a rigorous trade study. The legs seen in the slide will be attached to the vehicle and will provide support to the structure while on the surface, keeping the vehicle approximately 1 meter above the ground. A ladder will be later introduced. The finite element analysis was performed in pattern for convenience purposes. The three main structures to be analyzed are the tanks and the fuselage. The purpose of this study is to determine the accuracy of the previously done calculations and to determine if the vehicle is going to be structurally stable. Some errors may appear in the simulation, but they can be improved later on as details have not been set strictly yet. The team opted for a mesh seed of 5 points per element, using an isogrid for better analysis of the forces being translated throughout the larger surfaces of the vehicle, as well as to acquire more randomly placed reading points in case of any sudden failures in the structure. Despite the model only having a couple panels with color that show the displacement, that was due to an error while running the simulation. However, the animation of the whole structure showed an even distribution of the forces. The main structures of the Horus were composed of the skin, which is mentioned average thickness of 5 millimeters, ribs, which were placed in the main horizontal rings and had an average thickness of 15 millimeters, and beams that ran vertically from the nose until the bottom of the ship and that averaged 7 millimeters of thickness. The maximum and minimum displacement under the specific loads were between 10 and 30 centimeters. However, further studies with improved analysis might show an even bigger displacement. Computational fluid dynamics allows the launch's vehicle's aerodynamics drag to be defined by calculations obtained at zero yaw in an idealized environment. From this mission, CFD analysis will find various aspects of the fluid flow, including velocity profiles, pressure distributions, and other important parameters that govern the behavior of fluids in given systems. In this case, the CFD was performed using SOLIDWORKS, which allowed the team to change several key parameters that are not accounted for in a regular analysis. For example, changing the acceleration of gravity from 9.1 9.81 meters per second to 3.72 meters per second squared, setting the maximum velocity to 4,000 meters per second, and changing the atmosphere from air to a composite of carbon dioxide and nitrogen. In our case, the parameters for the atmosphere were 95% carbon dioxide and 5% nitrogen. While a regular Earth analysis is already set in the software, by changing the parameters to the ones in Mars, such as gravity, pressure, temperature, and the composition of its atmosphere, the fluids behave in a different way. In this case, the free stream velocity of the vehicle is set to 4,000 meters per second, since the planet is still significantly big, making the escape velocity to be supersonic. The analysis showed a decrease in the free stream velocity of because of the shock to almost half of the original velocity, but without any major perturbations that could affect the flight path. In terms of the temperature of the vehicle, the outer skin of the horse was designed to withstand major temperatures, mainly with Earth launch in mind. In reality, the mission will experience its hottest temperatures while departing our planet. But that does not mean that the ongoing mission will be much less intense, especially considering a key point, which is reusability. The friction between the air and the skin of the vehicle at such high speeds makes the temperature of the walls rise up to 6,500 degrees Kelvin or around 6,200 degrees Celsius. In addition to the temperature and the velocity of the vehicle, the stress caused due to these conditions is also something to consider. However, due to the other stresses presented to come out as a result of the thrust, weight of the structure, and the drag, the resulting stress from the CFD analysis turns out to be significantly insignificant, giving a maximum of 250 pascals. For the pressure experienced in the vehicle, it was mostly felt in the nose because of the direction of the free stream velocity, giving it a maximum pressure of around 80 kilopascals. While this number may be big, in reality, the pressure is not near the failure point for the structure, mainly because of the average atmospheric pressure is around 600 pascals. Regarding the max force obtained with the CFD, this graph shows the progression in the normal force and the average values recorded, coming a little bit over 1 million newtons. The reason for this immense force is due to the supersonic velocity of the vehicle as well as the great surface area the air is making contact with. In order to get a better result in the aerodynamics section of our mission, the CFD was helpful to obtain the max force and thus a more accurate coefficient of drag, which will help determine further improvements to our design. Moving on, despite this mission being this big and requiring a lot of its components to be large and resistant to the harsh conditions of space and other planets, there's still a great necessity for detail, especially when it comes to the electrical components, the avionics, and guidance systems, and the communication systems as well. In the following slides, I will be explaining in more detail the previous sections and their importance to the mission, as they have to be perfect in order to ensure safety and success. Let's dive into the electrical systems powering our Mars mission. They're the backbone of our operation, ensuring spacecraft functionality and communication with Earth. Our design prioritizes efficiency and reliability, crucial for the challenges of space travel. This section will include more detail on power generating systems, power distribution into the whole ship, electromagnetic protection in case of any incidents, and many other topics that may concern the efficiency and safety of the electrical systems on board. In order for us to determine the most suitable power generating system for the mission, A trade study was performed between polymer electrolyte membrane fuel cells, or PEM, hydrogen fuel cells, solar panels, and radioisotope thermoelectric generators, or RTG. The parameters were set to favor energy efficiency because, as engineers, we would always look for the most efficient solution to a problem. And in this case, if the power generating system is not as efficient as it could cost money, time, and even human casualties. Power density and usable life are next on the list, and they could also be considered a subsection of energy efficiency. However, these parameters need to be very precise, as the Horus is a highly calculated mission. And in order for the vehicle to have more room and a better chance of succeeding, power density and usable life are factors that also represent a huge deal breaker. Lastly, the cost of the system, while important, it is not as crucial as the other parameters have been. But that does not mean that the mission will spend all the money in just one section. As stated before, the Horus will be using 20% of NASA's yearly budget, and as part of being efficient, the team still has to ensure that we get the best option financially speaking, but with the other parameters still being a priority. In this slide, we have the unweighted as well as the weighted results of our trade study, giving us a result that the power generating system that the mission will use are fuel cells because of their efficiency, their high power density, and not to mention their reliability in space, accounting for their water recycling capabilities. The fuel cell system will produce electricity from chemical reactions, more specifically from hydrogen and oxygen. These cells also have the capability of turning the hydrogen and oxygen from electrochemical reactions into potable water that will be used to supply the ECLSS. Aside from the electrical components of the mission, the team also had to consider many precautionary methods to ensure the maximum safety of the vehicle while in space and Mars. According to the article by Alain Wang on Martian dust activities, Mars has shown to be subject to several lightning storms due to the recurring dust storms in the planet. It is because of the friction created by these dust storms and thanks to the thin atmosphere of the Martian surface that the energy cannot dissipate as easy as it would be here on Earth, therefore creating these powerful lightning storms that create a threat to our mission. Following NASA's Orion lightning protection, the Horus will overlay a conductive material, mainly as a physical layer of coating, to the surface of the dielectric materials, that being almost the entirety of our structure. Another method that the Horus will implement to avoid damages by lightning strikes is that the team will embed a conductive mesh as the first layer in the composite layer prior to the autoclaving. Since electricity does not flow in a straight path, this meshing will allow any major changes to the flow throughout the structure to avoid any major damages. Said conductive mesh is made out of polyester coated with nickel and copper and can provide high EMI shielding at a frequency range of 500 kilohertz to 10 gigahertz. EMPs, or electromagnetic pulses, are brief bursts of electromagnetic radiation that can harm or disable electronics. They can occur naturally, like during solar flares, or be caused by human-made sources, such as nuclear detonations. To ensure that the electronics of the mission are safe, the best way to protect them is by surrounding the launch vehicle with a Faraday cage. It will be made out of copper since it is a highly conductive material and will be grounded by connecting it to metal rods. The meshing and grounding of the cage allow for any unwanted electrical field to be distributed alongside the mesh and dissipated through the metal rods. Since EMPs are not the only threat in space, we also have to be prepared for other related complications, such as radiation. Radiation is a factor that should not be treated lightly, as any underestimation of it could fail the whole mission. Through the course of the space travel, the mission will encounter various types of levels of radiation such as galactic cosmic rays, or GCR, particles trapped in Earth's magnetic field, and residual radiation from solar flares. Considering the weight and usability of the mission, water is discarded from being used as a shielding despite its anti-radiation properties, and instead the Horus 1 will use traditional shielding made out of polyethylene. Polyethylene is a very effective material that, due to being highly hydrogenated, prevents nuclear fragmentation processes. In addition, it is easy to handle and manufacture, and it is relatively lightweight. This mission will use polyethylene with a thickness of 10 grams per centimeter squared, since it will provide a spacecraft with a 35 to 55% reduction in primarily gamma rays.
Moving on to the environment control and life support systems overview. So for our ecosystem, this is based off of International Space Station, actually. And so this diagram explains or adds a visual to how improvements will be made to the International Space Station's current ecosystem. So on the International Space Station, the system basically begins with the temperature and humidity control, where humidity and heat are removed from the cabin. Then air is mostly returned to the cabin, but a fraction is sent to the carbon dioxide removal assembly to remove carbon dioxide from the air. Then the carbon dioxide is sent to the CO2 management system for compression and storage. Moving through the carbon dioxide reduction system, water is recovered. Then the recovered water and water from the water processing assembly are used to generate oxygen in the oxygen generation assembly. The water processor assembly must provide purification from the temperature and humidity control system and the urine processor assembly. And then finally, there's trace contaminant control assembly that uses catalytic oxidizers and activated carbon dyes to remove contaminants from the air. So that's just a quick overview of the baseline ecosystem for our Martian transfer vehicle. So as we move on to more ECLS requirements, we're going to start with air supply. So to ensure that the crew can breathe in our Martian transfer vehicle, the ECLS system will provide an atmosphere similar to Earth. And this air supply will include 21% oxygen, 70% nitrogen, and 1% trace gases. And it's important to note that the cabin cannot be 100% oxygen to avoid a dangerous environment. And the interior would probably fall susceptible to fire, so we can't have that. Also, the cabin pressure will remain at 14.7 psi, which is similar to Earth. And considerations for the rate of air consumption reveal that a single human inhales the atmosphere at a daily rate of 0.84 kilograms, while respiring at 1 kilogram per day. This means that the air resupply system will be necessary to avoid total oxygen depletion. And by using electrolysis, the air supply system will produce 3.4 kilograms of oxygen per day. As far as trace contaminant control goes, there is potential for the crews to be endangered by unexpected accumulation of gaseous trace contaminants. So water vapor and carbon dioxide are the most significant atmospheric contaminants, so they must be closely monitored. And luckily, there can be some passive control with specific material selection and active control of onboard devices. So this assembly on the Martian transfer vehicle is designed to operate with limited power while still being reliable and requiring minimal maintenance. So by collecting samples of the air and analyzing for trace contaminants, this assembly will automatically adjust the vehicle's atmosphere continuously maintain safe conditions for the crew. As far as water supply and regeneration, Water is obviously necessary for any human survival no matter where they are. So without water, humans cannot survive longer than 3 days. And decision-making and concentration capabilities will be impaired even if there is a 2.5% loss of water in someone's body weight. And there's also a 35% chance of reduction in physical performance. So water is definitely necessary. The Sabatier method will be used to recover water, while a separate water processing assembly and urine processing assembly will be used to filter contaminants to generate water. And this combination of systems allows for the production of drinkable water and breathable oxygen. Now for food supply, food is necessary for the crew's survival, just like water, and food is also very important to have positive mental health effects, which means there needs to be a variety of eating options, both solid and liquid foods, rehydrated foods, natural form foods, frozen foods, fresh foods, all sorts of different types to keep up that positive mental health. Now for thermal regulation, to ensure safety of the crew again, the environment inside the Martian transport vehicle will resemble Earth, just as we had talked about a minute ago. So that means that temperatures will remain around 70 degrees Fahrenheit, with crew able to control this. It's necessary to take into account the various heat sources within this vehicle, including electrical systems, propulsion systems, and even crew body heat. So the orientation and location of the vehicle relative to the sun must also be taken into account in this case. And careful selection of materials is also going to be very important, as temperature gradients can change in just a matter of minutes on Mars. For sleeping arrangements, there really aren't very many sleeping arrangements because this is just a short-term transfer from the Martian vehicle to the orbiting station. So at those two places for sleeping will be established. As far as EVA capabilities, crew members may spend up to 24 hours a week performing these extra vehicle activities. So it's important to ensure their safety during these operations. And there will be a supply of spacesuits, each with an oxygen supply greater than necessary in case of emergencies. These spacesuits can also control temperature to prevent freezing or overheating. And with these features and many others, spacesuits will need power supply from our Eclipse module.
Have a better understanding of the whole electrical system and how it relates to other systems in the spacecraft, here is a block diagram to better explain the whole concept. To begin with, we have the fuel cells as our main power source, as they will provide with all the power to the different systems across the vehicle that are not the thrust. Branching from this block, we can find the primary components that will require the most power and that are crucial to the success of the mission. As you can see, the fuel cells feed to the payload, the propulsion, the launch vehicle operations, etc. Moving on from the payload, it will provide to the ECLSS, as well as the water collection system. This last one will be a major help in the longevity of the mission, as from this depends the power recycling and contribution back to the main source. For the propulsion, its two main components are the fuel consumption sensors, which ensure that the fuel is being used according to the calculations and is not being wasted, and the propulsion subsystems, which will ensure the stability and control of the Martian takeoff, as well as the orbital alignment in order to dock with the Martian space station properly. Lastly, the fuel cells will also power the most complex system in the whole ship, which is the launch vehicle operation. Not only does this control the communications and the GNC, but it also ensures the safety of the whole structure and the crew by sensing and modulating the temperature and pressure. Aside from the readings and the different sensors that this system handles, it is not just a one-way street, as some of these subsystems depend on feeding back to the main control so that it can continue to modulate in real-time readings.
Now for our final overview of this mission. So the vehicle has been designed as a transport spacecraft between the Martian surface and an orbiting space station. So we discussed that initially supplies and other resources will be sent to Mars utilizing the Starship Super Heavy launch vehicle before we send up humans to Mars. So for this flight test plan, before we can even get there, we have to test our vehicle. So structural testing will begin in 2026 and move through avionics, propulsion, environmental, flight termination, subscale flight, and full system testing before test flight by 2035.
To finalize this presentation, here is an overview on the CAD designs. The CAD designs show the clear vision of the structure as well as the insides of the Horus 1, consisting of the 2 Raptor engines, the 4 methane tanks, and the liquid oxygen tank. This has been all for Team 14. Thank you for your time, and War Eagle.